Aloha, everybody. This is Gigi from Kauai Community College. This is a video on optimization. And the idea of optimization is when you have a constraint, some sort of restriction that you have to stay within, and then you want to maximize or minimize something. Okay, so for example, here we are building a box. And so I have a picture of a box there for you. And as soon as you read this, you would think, okay, well, what properties have to do with a box? I mean, there's only really two things here, surface area and volume, right? So you would probably already in your mind thinking, well, I got to do something with the surface area and volume. All right. Now, this said, looking from the top down, the price of the top and bottom material is $15 per square inch. Okay, so the price of the top and bottom is $15 per square inch. So square inch tells you that this is dealing with area. So we're thinking now, as soon as I read that, thinking, well, okay, so that's probably, we're going to have to go ahead and write down what it means to have a surface area, right? But let's keep reading. And then here, the material on the side would be $3 per square inch for the side. Okay, now, you also want the length, base length to be 6 times the base width. Yeah, that's a mouthful. Okay, the length, base length, which is this right here, needs to be 6 times the base width. Okay, so as soon as I read that, I'm going to go ahead and call this x. And if I call that x, this is going to be 6x. Okay, so that's what we have so far. Now the enclosed volume has to be, the enclosed volume to be 20 cubic inches. So that right there is your constraint. You want the volume. So your constraint is that the volume has to be 20 cubic inches. And that's, do not write down cubic inches, just go inches cube. Okay, so far so good. Okay, now what do we want to do? What dimensions will minimize the cost? Well, so we want to minimize the cost. Well, so how is the cost associated with this? The cost depends on, the cost of material will depend on the surface area. The area of the bottom, the top, which has a different price than the material on the sides, right? So when calculating the cost, we have to separate it into two parts, top, bottom, and then the sidewalls. Okay, so far, that's what we have. Okay, now what other variable in this box that we haven't really named? This one right here. And let's call that y. That's the height. Okay, so let's call that y. So this is y. And this is x still, and this is 6x, right? So that's how it goes, right? That's just too busy, so I'm going to go ahead and erase those for now. Eraser. Erase these for now. Okay. So far, so good. That is all the information that are given. So now what you'll need to do is just to go and set up the problem, right? Easy said than done. What does it mean to just set up the problem? So we know the constraint, which is the volume, has to be 20, and the volume is length times width times height for a rectangular box. Or we would say area of the base shape, which in this case, the base shape has an area of 6x multiplied to x, which is 6x squared, multiplied by how tall, right? volume is area of the base shape multiplied by how tall. So that would be 6x squared y. Okay, so that's all we have so far. Okay, so the constraint, let's just go ahead and remind ourselves here. The constraint is 20 inches cubed, and that 20 inches cubed equals 6x squared y. Okay, we're just going to leave it there. And we're going to go ahead. Now we're going to go ahead and write down what it means for the cost. So the cost is going to be $10 for top and bottom, plus $3 for the size. Okay, top and bottom would be this rectangle here, and that rectangle has an area of x by 6x, and so is the bottom. X times 6x is 6x squared. Okay, and then so top and bottom 6x squared and another 6x squared, that's going to be 12x squared, and it's going to cost $10 per square foot for 12x square foot. Plus the side, well, we have 4 sides there, $3. Okay, so let's look at the side. What side do we have? We will have in terms of the side, we will have xy, and then we will have 6xy. Okay, we have 2 of those xy. That's the front and the back. And then you'll have 2 of the 6xy, so that would be 12xy. That would be the left and the right side. Okay, so then let's simplify that and see what we got here. We want to minimize the cost, and wouldn't it be nice if the cost was just in terms of x, right? So let's clean this up a little bit. Cost function is 10 multiplied by 12 is 120x squared plus 3 times, this right here can be combined, that's 14xy multiplied by 3, that's 42xy. And notice I just kind of dropped the unit so that it looked nice and clean. Now, I said, wouldn't it be nice if the function was just in terms of x? So let's go and do a substitution. So from here, we know y will be 20 divided by 6x squared reduced to be 10 over 3x squared. That is going to be your y. So you're going to go ahead and put that right there. Okay, so we will see then when we clean that up, the cost function in terms of x will be 120x squared plus 42x multiplied by 10 over 3x squared. The 3 gonna get divided out, and we will get, and then the x, one of the x is gonna get divided out. We'll get 140 over x. This is the function we want to minimize. So we want to know what is the minimum x value of this function. Okay, and that would be what's the minimum width. And then from there we can find the length, and then we can find out the height. So that is how an optimization problem will work. We will start with a constraint, and then we'll realize what we need to minimize or maximize. Use the constraint to your advantage here, meaning we're going to use it to do that little substitution so that we get a function just in terms of x. And then we want to now know what the minimum is. And to know what the minimum is, then we'll just use our calculus here. Take the first derivative, find the critical values, and then I think in this case, we are only interested in knowing if that critical value is a minimum or not. So we can just use the second derivative to test that. Okay, the second derivative test would be appropriate here. After you take the first derivative and find your critical point, because we're only interested in that particular point. Is that a maximum or minimum? All right, so let's see what I mean by that. Okay, so what I mean by that now is we're going to go ahead and take the derivative. First derivative is 240x, and then 140 divided by x is 140 multiplied by x to the -1 power, right? So when you take the derivative, you would move that exponent down. That's the polynomial rule, right? The power rule. Move that down, multiply, and subtract 1. You're going to have 140x to the -2 negative, which you can write minus 140 divided by x squared. Okay, so this is my thought process over here. Okay, now what do we want to do with this? We want to find out what is our critical point. Well, the critical point is x cannot be 0, first of all, otherwise the derivative will not be defined. But we know x is not 0. If x is 0, you wouldn't have a box. Okay, so we know that because this is a real life scenario, and we know x is not 0. So now we just go and look to see when the first derivative is 0. Okay, so that requires you to do some algebra here. To clear fractions, multiply everything by x squared. To clear fractions. And so you will have 240x to the third minus 140 equals 0. This is an onion problem. Go ahead and minus 140 divided by 240, and then take the cube root. So x to the third power is going to be 140 divided by 240. Then we will go ahead and undo cube by taking cube root, right? So then x will equal 2, and then reduce 140 over 240. You have cube root of 7/8. And this value is approximately 0.96, but just leave that there for now. I wanted to make sure we have the unit to see if it makes sense later. But for now, we're just going to use that exact value right there. That's our critical point. Now, what do we want to do at that critical point? Well, we want to know, hey, is that going to give me a maximum or a minimum? So we're going to go ahead and find the second derivative. The second derivative is going to be 240x, right? And then here, negative 140 times x to the -2. Then if we keep taking the derivative, we move this exponent down. So that would be 280 positive x to the -3, which we can write at 280 divided by x to the third. Okay, now the second derivative test said if the second derivative at that point, and that point is the 0.7 cube root of 7/8 at that critical point, if that second derivative is positive, well, let's just say, or is it negative, and then we can determine if it's going to be a minimum or not. 240, and I really don't have to do the math here, but I'm just going to write it down so you can see, plus 280 divided by cube root of 7/8 to the third power. You can see that all of these are going to be positive, right? So this is greater than 0, and greater than second derivative at that point is greater than 0. Then we know at that point, cube root of 7/8, at that point, our function is concaving up. And if our function is concaving up, then at that point, we would say that is our minimum. All right, so we just confirmed that this value right here is going to minimize our function, right? So what do we need to do next? We will just have to go and find what the other values are. So, so we would say now y is equal to 10 over 3 cube root of, remember what that was, right? 3 cube root of 7/8 squared, 3x squared on the bottom, 3 cube root of 7/8 squared, okay? And that would be your y. I mean, not your y, but yeah, that is your y. And then the other one would be 6 times it. So anyways, I typed that all into decimals, and we will get these values here. So we will see that our box would have a height of a width of approximately 9.6. Okay, so let me just draw that box again. That box right here, and then we have that length that is 6 times it, right? And then we have the height. I'm just trying to draw that box there. Okay, so now what we will have is to minimize that box. This would be approximately 0.96 inch, and then this would be 6 times it. So this is roughly 5.74 inch, and then the height would be 10 divided, this is your height right here, and then when we type that into our calculator, this should be 3.64 roughly inch. And of course that is not to scale, but if you build that box that way, you will have minimized your cost, and the volume will still stay 20 cubic inches. And if you can see, I check right here when I plug in all those values, volume is staying at 20 cubic inches. So optimization, let's go ahead and give it a summary here. Of course, you're going to have to read your problem first, right? But we'll need to look at the constraint and then figure out what we need to minimize or maximize and write a function for that. And you may need to do a substitution for that to be one variable. And once you have that function in just one variable, you proceed and find your critical point and then check if that critical point is a maximum or minimum. So maybe the hardest part in this problem isn't the calculus, but it is to understand the problem and be able to write your function. So keep practicing, keep getting the idea, and let me know if you need any help. You can always send me an email. We can meet up and address whatever issues you might have. Okay.